Well, thank you for that introduction, and thank you all for coming to the talk. So my name is Joe Ross. I work at Splunk. Fortunately, I think some of the previous talks here have sort of hinted at the general topics of quantile estimation and service level things that are sort of a consequence of that. So that's a little bit fortunate. Somewhat less fortunate is that before yesterday afternoon session, I had already put this parade of logos slide, so I'm a little bit bashful about trying to follow that act. But anyway, I used to work in pure mathematics. I spent some time at Signal Effects, and for the last pandemic or so, I've been working at Splunk. And now we have to stare at this for a few seconds. Okay, moving right along. Okay, so I'd like to sort of formulate the core mathematical or statistical problem that I'll be focusing on. So it's given a stream of numbers, x1, x2, and so on, to build a data structure that can answer rank queries, and where the rank of some number is simply the number of stream elements that are less than or equal to that number. A related quantity is the quantile of the stream. So here q is the number between 0 and 1. And this just asks for some number whose rank is exactly that number q times the stream length. Right? So if q is equal to 0.5, then we're just talking about the median. So there are some requirements you might ask for this data structure to satisfy. So one is that it should operate online, meaning that it processes the stream exactly once. Another thing you might ask for is that the size of the data structure should have a mild dependence on the stream length, which, by the way, is not known or bounded in advance. So we certainly don't want to store the whole stream. Ideally, we have logarithmic, or maybe even something smaller than that, dependence on the stream length. And of course, we also want the update operation, which says, I have a data structure, a new point has arrived, I'd like to incorporate that, the sort of add operation, and also the rank and quantile query operations should be fast. So the sort of routine application is to service level, objective, and agreement, so on, monitoring. And I think we've seen this on a bunch of slides. But for example, over the last month, I would like to know if I've served some very high proportion of requests within some agreed upon threshold. Right? And you can also imagine sort of turning this into an anomaly detection problem where you compare maybe the last day to the last month or the preceding month. And if you think about metrics other than latency measurements, you can sort of see this as a foundational building block of an anomaly detection system in general. So sort of using these quantiles over time to form baselines for metrics. Okay, so the first results in this general field basically say that if you want to answer quantile queries exactly and you want to have mild dependence on n, then you're out of luck. So Munro and Patterson proved that for an algorithm that passes over the data p times, if you want to answer rank and quantile queries exactly, you'll need at least the pth root of the stream length size in order to do this. And so in particular, if you want to answer queries exactly in the online setting, which is where p is equal to 1, you'll need to store the whole stream, or a data structure of at least that size. And it's actually a kind of nice so-called white box argument. So you imagine that you have a buffer of some size, so say size S. You're kind of sweeping through the stream. A new point arrives, say the buffer is full, a new point arrives, somebody is going to get kicked out because you only have size S. Now you just arrange that the next element that arrives in the stream, in terms of the items that you still have, has the same rank as the one you just kicked out. Okay? So in terms of the information that you actually have at that point, you have no way of comparing the thing that just arrived and the thing you just kicked out. And so somewhere in the quantile space, you'll have a problem of at least size n divided by s. Right? And so if you keep doing this, what you see is that you'll need at least the pth root of the stream length if you want to answer rank or quantile queries exactly. Okay? And this sort of leads us to formulate an approximate version. So if you want this requirement of mild dependence on n, then you'll also have to ask for some, you'll have to allow for some relaxation. And so you might say that I don't need to return the rank or quantile exactly, but I'd like to do it within some bounded error. So give me an approximate rank, rank hat, that differs from the actual rank by some error epsilon. right? So if epsilon is 0.01, then I'd like my answer for the 95th percentile should be somewhere between the 94th and the 96th percentile. Okay, I'll just make a few comments about what this condition actually means. I think there may be some confusions about this. So maybe the most important thing is that the error condition is formulated in quantile space, not value space. In other words, the estimate has to be between, of the 95th percentile, has to be between the actual 94th and 96th. We are not requiring that the estimated 95th percentile is within 1%, like 1% in milliseconds, for example, of the true 95th percentile. And this may seem a little bit odd, and if you think it's odd, I probably won't convince you that it's not odd with 4 bullet points, but anyway, I'll just kind of say them, and maybe you'll feel differently when you wake up tomorrow. So one is that this is a formulation that makes sense for streams drawn from arbitrary ordered sets. So we generally think about numbers, but actually these data structures would also work for strings, for example, lexicographically ordered. This formulation also has the nice property that is invariant under monotonic transformations, right? So if somebody is seeing some stream x1, x2, and so on, and somebody else is seeing a stream, 100 plus x1, 100 plus x2, and so on, the sort of answers that they'll give if you subtract 100 from the person who's seeing that translated stream will be the same. Whereas if you use a data structure that has guarantees in value space, the answers that they give and the qualitative statements that they can make are actually rather different. So it's a little bit awkward. It's also the case that the problem for guarantees in value space has several simple solutions. So basically, if you're interested in relative error bounds in value space, you can just use logarithmic histograms, right? It's not really that much controversy. Like we don't need to write any papers about this. It's fairly straightforward. And then perhaps most amusing, guarantees in quantile space can be arbitrarily bad in value space and vice versa, right? So these are sort of just different problems, right? So if you have some histogram and all of the values are sitting in a single bucket, you can't actually say, and you don't actually have any guarantees in quantile space. Right, and similarly for these data structures, in general, you don't have any guarantees in value space. Although in practice, you can kind of see some correlations, although this is very data dependent. Okay, so another aspect that we like to have is that the data structure is mergeable, and that means that if we make one of these D1 on a stream X1 and D2 on a stream X2, then we can define a new data structure, the merge of D1 and D2, which has similar error guarantees to those of D1 and D2. So it doesn't have to be the same as making the data structure on the union, but in terms of the error guarantees, it should be very hard to distinguish those two. Right, in terms of quantiles, if you sort of operate on the bottom row of this diagram, if you know the quantile of some set x1 and another one x2, you know that the quantile of the union lies between these, but otherwise you can't really make any guarantees. Whereas if you operate in this sort of richer space of these data structures, which we'll get into shortly, you can merge these two and still extract the quantile with some guarantees. Okay, I'll just pause for 5 seconds to see if there are any questions at this point. Okay, yeah, so I give a bunch of talks at virtual conferences, and there are the problems that you're sort of talking into your monitor and you have no idea whether or not the audience is following. And so now I actually have the same experience of not knowing whether or not the audience is following, but I'm up on the stage. So just sort of forgetting the requirement that we operate online. Imagine, just as a sort of thought experiment, that you could store the whole stream, right? So someone's going to say, I'm going to throw a bunch of numbers at you, and then you don't have to operate online, you can store everything, but after that, I would like you to make a very compact read-only data structure that can answer rank and quantile queries, right? And let's say I tell you epsilon is 0.01, right? So what you would do is, let's say I give you 7,000 elements, you store them, you sort them, right? And then you would take every 70th element, right? And that would guarantee that if I give you some element, you just find its neighbors, if you want to, and then you count how many are to the left and to the right. That'll tell you the rank. And if you want to know a quantile, you just sort of travel along this list of sorted elements. And so generally speaking, all of the data structures that we'll discuss are trying to do this sort of sampling across quantile space evenly. The problem is that you're not actually able to store the whole stream. And so when you keep an element, you have to have some concept of its rank, or how many elements are to its left and to its right. And this is sort of the fundamental problem that all these data structures are trying to solve. So how do we achieve this when we're not actually able to store the whole stream? Okay, so the first data structure in this direction was invented by Greenwald and Khanna, and it maintains a set of triples. So V is some element that's sampled from the stream. There's a quantity G, which is the difference between some bound on the rank of that element, the difference between that and a bound on the rank of the preceding element that you've stored, and another auxiliary quantity called delta, which is basically a difference between an upper bound and a lower bound on the rank of that element. And so if you think about it, you really just want to store the difference between, you just want to store, you want to basically get a sense of how many elements could be to the left or to the right, and it just turns out to make the mechanics work, it's a little bit easier to store these auxiliary quantities rather than Rmin and Rmax themselves. Right, and so if you ask what the error is, it turns out that it's bounded by the largest over the elements that you've kept, 1/2 the sum of gi and delta I. You can sort of work this out with some simple algebra. You'd like to be able to insert things. So if you have a new element, you insert the triple V1 and then the floor of twice epsilon times the stream length. And so you'll get a bunch of elements. You'll have a bunch of V's, 1s, twice epsilon times something, and then eventually you'll have too many things. So periodically you sweep over this collection and you try to merge triples in such a way that the sum of G and delta is basically twice epsilon, which is your error target, times the stream length, right? And so when you do this merging, the G's add. And the delta is basically the sum of G plus delta, right? So there's a little bit of interaction between those terms. And it turns out that this data structure can answer rank queries with the prescribed error epsilon, right? So you don't have to specify any bins. You just say, this is the error I want. You'll get a data structure that can do this, and it requires the space listed here. The unfortunate thing is that this structure is not known to be mergeable, and it's suspected that it cannot be merged. Okay, so there's a sort of variation on that, which is called the KLL sketch. And this is, again, a sampling device that's very careful and hierarchical. So the core structure inside the KLL sketch is called a compactor. And this is basically a collection of K items in order. And they each have some weight W, which represents how many elements they're standing for. Okay, so it's just a bunch of elements with some weights. And what you can do to this thing is, well, you can compact it, and that means you can produce something which has half as many elements with twice the weight. Okay, and when you actually do this, you keep the even or the odd elements with equal probability. Okay, so here's a picture. So I have this compactor. It's got the elements A through F. They each have some weight W, and someone says, hey, compact yourself. And I say, okay, well, now I'm B, D, and F, each with weight 2W. Okay, and so all we're going to do is basically arrange a bunch of these in some hierarchy. So a bunch of stream elements are going to arrive. We're going to keep them in sorted order. So we have K of them. The next one arrives, and we ran out of space in this level. So what do? Well, we perform a compaction. So now all of a sudden we have half as many elements, and we have to pass them up to the next level. So at that point, we have this next buffer, or this next compactor, is a little bit less than half full, and we've got a single element sitting in level 1. Right, so more elements will arrive. The compactor in that level 1 will again fill up. We'll perform a compaction, pass all of them to the next level. Eventually, level 2 will fill up, and so on. Right, and so we'll eventually have to make some large number of levels. But this is sort of the core idea. And then, I mean, the description is not that hard. What is maybe a little bit more difficult is actually analyzing the error in this data structure, which you can do using Höffding's lemma. And then there are a bunch of optimizations that these authors came up with. You can sort of replace the low weight compactors with sampling, right? And then you have to treat the heavier compactors with a little bit more care. But eventually, if you use some randomization, you can get this data structure down to the optimal size, which is the order 1 over epsilon. And this has the nice property that it's mergeable, right? To do that, you just concatenate in each level and then perform a sorting. Okay, so that's very nice. Any questions about this? Okay, so again, it's sort of like motivated by the Greenwald kind of thing, but it's a little bit simpler conceptually, and the sort of statistical analysis that studies its error is actually just a few pages. So it's really a nice conceptual advance. Okay, and so we often care about latency distributions. And here, you might care a lot about the difference between the 95th and the 96th, or even the 99th and the 99.5 percentile. But you really don't care that much about, say, the difference between the 50th and the 51st percentile. Right? And so if you're interested in the tails of a distribution, which I think in many operational scenarios is the case, you might want a different concept of error that this data structure should try to meet. And so this is formulated as a relative error. And basically it says, so one way to think about it is you have a bound on not the difference between the estimated and the true rank, but rather the ratio of the estimated and the true rank. Or you can say that this difference is bounded by epsilon times the smaller of the rank and the stream length minus the rank, depending on whether you're near the minimum or you're near the maximum. And of course, this is a strictly harder problem than the original epsilon approximate condition that we had, right? Because the rank and n minus the rank are obviously smaller than the stream length n, right? And so it will turn out that solving this problem provably requires more space. Okay, and so one data structure that really tries to bring this concept of relative error and even generalizations to the forefront is the t-digest of Dunning and Ertl. And so the basic idea is that we maintain a sorted list of centroids, CW, which represents W points near some number C. And there's one variant where you're basically performing incremental clustering. So you have this collection of centroids, a new point arrives, you find this closest centroid. If it has space, you add it. If it doesn't have space, you form a new one, right? And then there's a merging variant, which uses arrays, has a sort of buffer of things that you need to incorporate. And this one actually avoids dynamic allocations in the implementation of Dunning's t-digest library, although it does have some slight accuracy issues on some streams. And the thing that sort of makes this go is the concept of a scale function. And this is basically a function from quantile space to the extended real line, which says how accurate do I have to be as a function of where I am in quantile space. Okay? And there's also a compression parameter called delta, which basically controls the number of centroids that this data structure will have. So it controls the size. And the condition is that if you have a cluster or a centroid that occupies some region in quantile space, say Q1 to Q2, then when you apply the scale function k and look at the difference between the endpoints, that difference can be at most 1 over delta, right? Or the cluster can consist of a single point. So in the case where you have a linear scale function, then you're basically asking for the cluster size to be constant in Q, and that corresponds to the original epsilon approximate condition, where you ask for 1% error in quantile space everywhere in the distribution. It gets a little bit more interesting when you start writing down fancier scale functions. So this one is from Dunning's paper, so it's the log of Q over 1 minus Q. And as you can see, it's sort of increasing very rapidly near 0 and 1. And if you look at 1 over the derivative of the scale function, that basically describes the cluster size. So we're allowing for fairly large clusters in the middle of the distribution, where we don't care that much about accuracy in some operational scenarios, but we're asking for relatively small clusters near Q equals 0 and Q equals 1. So we can expect our answers to be much more accurate in those parts of the distribution. Okay. And so it turns out that the mergeability of a t-digest can actually be translated to an explicit analytical condition on the scale function. Right? So basically you have some little cluster inside quantile space. When you make an insertion or merge with another one, it's going to slide around a little bit. And you have to make sure that when it slides around, all of a sudden the space that it occupies with respect to the y-axis, so to speak, doesn't become too big. Okay? And so you can write down some condition. It's a bunch of inequalities. And then you can actually show, using this condition, that differentiability is required. So if your scale function has any place where it sort of looks like this, which is what it looks like if you zoom in small enough, then you'll be able to realize some insertion or some merging where that requirement on the case size of the cluster will become violated when you sort of move over to the region where the derivative is larger. Okay, and there are many scenarios. So all of the original scale functions had a symmetry about the q equals half line, and there are many scenarios where we care very much about the quantiles near q equals 1, but we don't really care about quantiles near q equals 0. Right? And if you sort of look at the explicit condition that you can derive analytically, and also the requirement of differentiability, you're sort of naturally led to a construction which basically says, well, I don't want to use the original left half of the function k2, for example, but I want to keep differentiability. How about I just replace that part of the graph with its tangent line, right, and extend that? And that corresponds to keeping the cluster size relatively large on exactly 1/2 of the distribution. And it turns out this sort of works in the sense that if you make this construction on any of the known scale functions, you preserve the mergeability property. Okay, so this gives you, so roughly speaking, this allows you to reduce the size of a t-digest by 40% and have basically the same accuracy near q is equal to 1. Of course, you have less accuracy near q is equal to 0, but you didn't really care about that, and you maintain the mergeability aspect. Okay. And then there's a sort of a variation of the KLL sketch, which did this compaction thing, where if you think about this cluster size, if you sort of invert that, you could think of that as describing a sampling intensity, right? And so the idea of the relative error quantile sketch is to just make a compactor that doesn't sample uniformly, right? And so this is kind of a cartoon of it, but basically on the left-hand side, there'll be some little chunk of the compactor that always participates in removing half of its elements. And then the next little segment will have half of its elements removed half of the time. And then the next segment will have half of elements removed only a quarter of the time. And then the right half of the distribution will never be involved in a compaction. Okay, and then there's kind of a similar hierarchy. Actually, the definition is not too much more involved, but the analysis is a lot more delicate. It takes like many pages instead of just 1 or 2. And the resulting sketch is quite a bit larger, as you can imagine, since there's basically half of the stream that we're never sampling from. But this is provably needed, which you can maybe guess from the difficulty of the relative error condition. Okay, so I submitted this a couple years ago. And I actually had at Splunk, there were some other people who knew about this problem, and I ended up being introduced to some of the people in the KLL circle, and we tried to do a comparison of the rec sketch and the t-digest, and we basically yielded some of the theoretical arguments for the rec sketch against some very detailed knowledge of how the t-digest works internally to come up with some adversarial examples for the t-digest. So I don't know, I love this stuff. So let me try to explain how the t-digest might make errors for you. Okay, so there are basically 2 sources of errors, and we're going to combine them. Okay, so as I sort of mentioned, in this t-digest scenario, we have a bunch of elements. Periodically, we sweep over them and take the average of a bunch of points, sort of weighted average, and use that as the centroid representing that collection of data. Okay, so there's one situation which is not so great for this, which is if you happen to have a centroid that represents a single point x1 and then many copies of the same point x2, which is equal to x3, so on, then if you ask for the rank of some element between c1 and x2, you only have c1, right? You threw away the x's. You think this point is bigger than c1, but it's actually less than almost all of the points that are represented by c1. So that's not great. Okay, so the mean can be very different from the median in a single centroid. And the other problem is that since you only have the centroids, and those are ordered, those are ordered, but they're only weakly ordered. So you know how the centroids compare, but you don't understand how the data sets that contributed to those centroids actually compare. So in the top line, we have the same lopsided centroid from the previous slide. Now imagine you sort of, you got this knife in there, you're just twisting it, right? So you find this place where there's a bunch of error. What do? You do the same thing over again, right? So you make another lopsided insertion. Now I'm calling them y1, and then a bunch of copies of a point y2, right? So again, you have another lopsided centroid. So now imagine someone asks you we ask this digest for the rank of some element between c2 and y2. Okay, so as far as the digest is concerned, we only have the red stuff. right? So we think it's bigger than C1 and bigger than C2, but if we had the whole stream, we would realize that actually this point is less than almost everything that contributed to those centroids, right? So it's less than Y2 and it's less than X2. And so, this is kind of the idea. It takes a lot of, it takes some work to actually make this precise. But the sort of punchline is that you can realize this attack on most of the implementations of T-digest, and just having more centroids or increasing delta doesn't really help you. There's also a formulation where you can just write down a distribution that uses kind of mixed scales. Okay, do I have a minute left? Okay. All right. Any questions about this? Okay. Okay, and then the last approach I want to mention is a bit different. So this is not really trying to do any sampling. It's more, I say, classically statistically based. It's called the moment-based quantile sketch. And so just as maybe it's called a straw man. Just imagine we're a little bit lazy. We have some package that will compute for us the rolling mean and the rolling variance or standard deviation. Well, one thing we might do is just say, maybe my data is normally distributed, which could be the case. I mean, it's definitely not, but it could be the case. And then use its quantiles, right? Use the quantiles of the normal distribution to estimate the quantile of the actual stream, right? Or to answer rank queries. Okay, well, I think we can all come up with counterexamples to this. I mean, it sort of shows up on any slide involving latency distributions, right? So here's a pair of distributions which have the same mean and the same standard deviation, right? Of course, they're quite different. And if you just use quantiles of one, you will not accurately estimate quantiles of the other. Okay, but I know how to tell these apart, right? But this is not me, this is somebody else, but I know how to tell these apart. I know that the one on the left, which maybe looks more like a latency distribution, is skewed, right? The one on the right has no skew, right? And the skew is, just as the variance you could think of as the average of the squared distance to the mean. The skew is basically the average of the cubed distance to the mean. Okay, you're supposed to divide it by something, but morally this is what it is. And so if you analyze this quantity on the left, you'll get something positive, and if you analyze this quantity on the right, you'll get 0. Okay? So then the question becomes, well, if I know the mean and standard deviation, I can write down the normal distribution. If I know the mean and the standard deviation or the variance and the skew and the kurtosis, and then the next of these sort of centered normalized moments, however they're called, how do I write down a distribution so that I can use its quantiles to estimate the quantiles of the stream? Okay? And one way to think about this is, well, if I have this pair, mu and sigma, how do I characterize the operation of taking the normal distribution? Well, one way to describe it is that you are picking the distribution with the largest entropy, realizing those two moments, right? Among all distributions with a fixed mean and standard deviation, the normal distribution, in a sense, is the least informative, right? So it has the highest entropy. And so this is the sort of thing that generalizes well to this scenario where you have multiple center normalized moments, right? So you ask for the distribution which has the largest entropy, subject to the constraint that it realizes a certain collection of statistical moments. And it turns out the solution to this can be drawn from an exponential family, which has a very efficient numerical solution. And in terms of observability, maybe the interesting thing is that the merge operation can be vectorized, right? So you don't actually store the mean and the standard deviation. You have to do something a little bit fancier, like conceptually you're keeping the count and the sum of squares and so on, but you do it in a numerically stable way. But the merge operation can be expressed in terms of first adding a bunch of vectors together and then doing a little bit of math and then solving this problem and then finding this distribution from the exponential family. So if you ask for some quantiles over a very large number of combinations of some attributes and possibly over time, and you have to do millions of merges, this is something you can actually do efficiently. And there's I think it's called a plugin or an operator for Druid that implements this moment-based quantile sketch. Whereas if you use something like the KLL sketch or the T-digest or any of those variants, when you do a merge operation, you're basically merging two sorted lists. And this is something that you usually can't do very efficiently if you have millions of such lists. So for some scenarios, this approach, while it doesn't have theoretical guarantees, has some very attractive qualities. And that's it.
Awesome. Well, whenever people sometimes conference talks at monitoring events are they're too high level, they're too forward thinking. I will always point them to Joe's talk, which always makes me think, I was told there'd be no math. Anyway, we do have time for any questions from the audience. Yeah, got one right here.
So, do you have an opinion on what observability systems, which of these techniques we should use, and how much would it cost us to implement something good for latency, for example? If we want the 99.99 percentile, how much storage would it need?
So what the techniques would be and the cost.
Yeah, no, that's a great question. So in terms of the cost, I don't think I can say anything definitive right now. In terms of the maturity of these various data structures, the KLL sketch it has an implementation in the Data Sketches Apache project, which I believe has been pretty well tested. The rec sketch, I think, would be more suitable for observability use cases where you care about these quantiles near Q equals 1. So I haven't actually looked into this in the last few months, but I believe that hasn't been quite as battle tested. It's sort of based on the same code base, but I presume there are a lot of edge cases that we maybe haven't really analyzed in the wild. So I would hope that eventually, if cost permits, that we could use something like the rec sketch, relative error quantile sketch. There's this kind of thing that's waiting for you, which is if you want the data structure to have a fixed size, which I think everybody wants, you cannot actually have any guarantees on the error, right? So like the KLL sketch and the rec sketch there's always some logarithmic factor, right? And it's kind of just waiting for you as an inherent difficulty in the problem, right?
All right. Is there another question out there? Up top? I just want to call out too that it's always fascinating to see in different slide presentation systems. This is all in a Jupyter notebook, right?
Yeah, Jupyter notebook slides, yeah.
Which is just, again, incredible stuff. So great. Thank you again. Big round of applause for Joe.